Hello students. So today we'll talk about behavior of gases. As we all know that states of matter is going to be the central portion of physical chemistry. So we will start our study of states of matter with the study of behavior of gases. These principles will be used in thermodynamics. These properties of gases can be used to solve numericals in equilibrium and for further parts of physical chemistry. And why is it so? Because gases is the only state of matter for which we have a proper model system. Fine. You may say that's why we studied a lot about solid state in recent few years, but still we have a proper model system for gases. So this is the foundation, and we still to understand a whole lot of things about liquid systems. So gases will be the central part. So now let's start our session for today. So students, first of all, before we enter this part of physical chemistry, we must be aware of the measurable properties of gases. So how can we find out the measurable property? Which are these properties? So number one, we'll talk about the measurable properties. And first of all, amount of the gas. Now you can find out the moles, the amount of the gas. So this is the first measurable property. So we will talk about moles of the gas, mass of the gas for a specific volume. So you can, if you want to find out the number of moles, then first of all, you need to find out the mass of specific volume of the gas system. Now, the next one will be volume. Now we have certain what is actually the volume is volume of the gas. But gas will certainly occupy the same volume as of the container. So we need to understand the different units which we will use for the calculation part of volume. So you can get this idea by just observing a water tanky on the roof of your apartment. So what you can think of, you know what, a water tanky of about sizes of 1 meter into 1 meter into 1 meter, the dimension of 1 meter, 1 meter, 1 meter. The water tank of this dimension can hold 1,000 liter of the water. So what we can say that 1 meter cube is equal to 1,000 liter. Most of the time, we must bother by this unit conversions. How many liter will constitute 1 meter cube? How many liter will constitute 1 dm cube? So this is a better way, by looking around. You can design, you can think, you can link various things. Daily life is a daily life, or the things in your daily life is basically a very good tool to understand the sciences. Just by looking at the water tank on the roof of your society, your house, your home, or maybe on the roof of your school. A water tank of the dimension 1 meter, 1 meter, 1 meter can hold 1,000 liter of water. So 1 meter cube is equal to 1,000 liter. Now, what can be 1 decimeter? So in 1 meter, we have 10 decimeter. So 10 decimeter into 10 decimeter will be equal to 1,000 liter. So 1 dm cube is equal to 1 liter. Isn't it? It's pretty easy to understand. Okay, so 1 dm cube is equal to 1 liter. What about centimeter? So now in this case, 100 centimeter into 100 centimeter will be equal to 1,000 liter. So 10 raised to the power 3 centimeter is equal to 1 liter. Fine. So my dear, this is what the concept of ml is. Now this is centimeter cube, cc. generally written as cc. Pretty easy, centimeter into centimeter into centimeter, as 1 dm cube is equal to 1 liter. 10 raised to the power 3 centimeter cube is equal to 1 liter. So this is cc or ml. So 1000 ml will be equal to 1 liter. So this is how we can actually convert the different units of volume. And volume, as we know, the gases, they occupy the same volume as that of a container. The next thing, which is pretty important, and that is pressure. And when we talk about pressure of a gas, then we must understand that this is the property, this is the measurable property, which is to be used in many aspects while defining a gas. How can we define pressure? Simply, we all know that pressure is force per unit area. Force per unit area. So by definition, the gas particles are actually moving away from each other. My dear student, in our gaseous state, as we all know that in all these three states of matter, we have different states of matter, like we have post-condensate, plasma, and other things. But majorly on Earth, and for the part of our studies, we consider three states of matter: solid, liquid, gas. In case of gases, under ideal condition, so we actually talking about the ideal gases. Under ideal condition, we believe that there is no interaction force between the gas particles. So if there is no interaction force, means there is no attraction or repulsion, whatever is it. So no interaction means nothing, like no attraction, no repulsion. So these particles are actually moving away from each other. Mind it, they are not just away from each other, they're actually moving away from each other. And while moving away from each other, if you want to contain that gas in a box or in a cylinder, so as these particles are moving away, so they will strike on the walls and create and exert a pressure. Now gravity for our, this is the smaller system when we are considering a gas inside a cylinder. So now let's talk about the force of gravity on Earth. Now, gravity is the responsible force which attracts the gases, air towards itself. And because of this, the atmospheric gases, it push, or what we can say, the Earth's surface where the gravity wants to pull it down. Now, these particles, these gas particles or the air particle, they will exert pressure on every object which come in contact while this air is attracted by the gravitational pull. So this is what the atmospheric pressure is. It's just like a blanket of gases. Just try to visualize. As gravity, the gravitational pull is exerting what you can see the attractive pressure to pull these atmospheric covering down. During this process, the gas particle will exert pressure in everything which comes in contact while they are coming down. So it's just like what you can say, like I said earlier, a blanket. And the pressure exerted by these forces, these particles, will considered as atmospheric pressure. So we can assume that pressure is basically the atmospheric pressure will be highest and maximum at the level of what we can say the sea level. And gradually, if we increase the altitude, as the gravitational pull becomes weaker, the density of the gas will again become less. Sir, are you suggesting a relationship between density and pressure? Maybe. Let's see through it. First of all, let's talk about pressure once again. So I believe you must be aware how important this pressure is. Without this pressure, we cannot breathe. Why, sir? You know what? This process of breathing involves the important role of pressure difference. We all know that diffusion will take place. In elementary biology till our class 10th, if you are preparing for sangharsh batch student, you are preparing for IIT JEE. But still, you have that elementary biology in your class 10th. And you must be aware of the fact that pressure difference is the cause of what breathing. So this pressure difference is pretty important. Even on Earth, the flow of winds is due to the pressure difference. You can very well know that while watching some news about monsoon, we generally observe that the news reader was saying that due to the pressure difference or the pressure variance, the monsoon will be a bit delayed or may come sooner. So these kind of things can happen because of this pressure. So as we can understand, the pressure is force per unit area. So let's talk about force first. F is equal to ma. Okay. So my dear student, how to calculate? Now we are talking about how to calculate pressure. And I'm going to use this F is equal to ma concept. But before that, let me introduce the barometer. Barometer is actually a device which is to be used to calculate pressure. And the simplest barometer was designed by Mr. Evangelista Torricelli. Mr. Torricelli. And you can actually observe this in your daily life while bathing in the morning. Let's say you have this bathtub full of water. Now you can put your mug inverted. First of all, fill your mug with water and then invert it down. And this was the water source, what you can say, the Jaguar bath fittings. And the pressure is coming down with full pressure. The water is coming down with full pressure. You must observe that somewhere down the line, when water is coming down with full pressure, the already stored water will rises up. Yes or no? So what we can say, the pressure which is coming down, so the pressure at this point or at this point will be same. Okay. So Torricelli will use this sort of philosophy and design one barometer. He uses a tub full of mercury. Mind it, mercury is actually a metal, exists in a liquid form. So this is the densest liquid. As it is a metal, so this is going to be the densest. And that is why in most of the cases, when we really want to measure pressure or temperature, we use this mercury. Because in case of, if we really want to use it to calculate temperature, so we know that because of uniform temperature coefficient, this is going to be the better choice. And again, this is the densest liquid. As it is a metal, this is the densest liquid. The density is the highest in this case, in case of mercury. And this is opaque. So if you want to measure it, because this is opaque, light cannot pass through it. So we can check, okay, this much is the level. If it is, light can easily go through it, and then we cannot measure it. Okay, because we need something. If it is opaque, that is why the taking reading is possible. So what Mr. Torricelli did, he actually took a tube, filled that tube with mercury, put his thumb over the top of that tube and invert that tube like this over this particular, what we can say, the tub full of mercury. Now, as atmospheric pressure will be applied directly. So the pressure at this point, the pressure at this point, and the pressure at this point will be same. As we can say, this is the horizontal surface and pressure will be same at each point. Fine. Any problem with this till this? If you really want to understand, you can pause this video for a while and again go through everything to understand it well, why pressure at one point is similar to or same to the pressure at the second point. Now we have to find out, as this tube is filled with mercury. So gradually this mercury is coming down and we can observe that The mercury is coming down, but up to a certain height. And why is it so? Because there is a pressure, that is atmospheric pressure, that is coming and will be applied directly on this water level. As you know that water is coming down and water level rises because of this pressure. So as this pressure, the pressure because of this liquid column and the pressure exerted exerted by the atmosphere, that is known as atmospheric pressure. When these two pressure becomes equal, this tube will have this much of height. And as mercury is pushing down, leaving this space behind as vacuum. Again, mind it, leaving this space behind as vacuum. So let's say this is the pressure at this point. At this point, the pressure is P1. At this point, the pressure is P2. And we can say that P2 is equal to P1. So the atmospheric pressure will be equal to the pressure exerted by this liquid column as well as this vacuum. Now we know that in vacuum, there will be no particles. They cannot exert any pressure. So this will be zero. And so the pressure exerted by this column will be equal to the atmospheric pressure. Now, my dear student, how can we find out the pressure exerted by a liquid column? Okay, so the question will be how to calculate the pressure exerted by a liquid column. Okay, now look at this. Let's come back to the concept of force is equal to ma. F is equal to ma. So now area will be volume into height. Look at this. Sorry, volume is equal to area into height. Okay, what we can say, volume is equal to area into height. A is simply the acceleration due to gravity. As I've already stated, the force of gravitation will pull, like the force of gravitation will pull that atmospheric gases towards itself. So we need to use this acceleration due to gravity in place of A. Now volume, that is the measurable property, that is area into height. So what we can assume that in place of mass, we can take density into volume. You know what? We're talking about the mass of a specific volume of the gas. So mass will be written as density into volume. Fine. So F is equal to density into volume into G. Now we know that pressure will be equal to force per unit area. So my force will be density, that is on most of the occasion will be represented as rho into volume into now this volume into G upon area. Can we further simplify it? Yes, by using volume is equal to area into height. So area into height into G upon area. You know why we were using this concept of volume? Number one, we want to calculate the mass of a specific volume of the gas. And if you really want to calculate the mass of a specific volume of the gas, then you must use density, because density will be equal to mass upon volume. So in place of mass, we must use density into volume. So now my F is equal to dV into G, as A will be replaced by G. As we all know that pressure is equal to force per unit area. So now force will be rho, that is density, into V, because we are talking about mass, and this will actually the factor for mass, into G upon area. If you really want to simplify it, rho into area into H into Z upon A. You can cancel out this. So the pressure can be calculated as rho Hg. Now, my dear student, how we can calculate it? The density of this mercury is 13,600 kg per meter cube. G will be taken as 10. So this is density of mercury. G 9.8, we will take 10. Okay, fine. It was observed that at sea level, the height of this mercury column is 76 centimeter or 760 millimeter. So at sea level, the height of the mercury column is 76 centimeter or 760 millimeter. My dear students, we all know that the pressure exerted by this liquid column will be equal to the atmospheric pressure. Fine. So what we can say by this thing, that 1 atmospheric will be equal to 76 centimeter of mercury or 760 millimeter of mercury. Mind it, pressure can never be equal to height because these two had different units. But what this signifies, that this pressure of 1 atm will be, now the pressure of 1 atm will be equal to the pressure exerted by a liquid column of height 76 centimeter of mercury at sea level. Many a time you can get this in inches also. So as we all know that 1 inch is near about 25 millimeter. So that is 29 point, maybe 89 something inches of mercury. This can also be used. These are just the unit conversion. And why I am discussing all these unit conversions? Because this is the major source by which you can commit a mistake. So now let's talk about the other units of pressure. So 1 atm will be equal to 760 millimeter of mercury or 76 centimeter. So as we can say that height will be 76 centimeter or 766 by 100 meter. Now, as density of mercury is this, so we can calculate in Newton per meter square. So the pressure can be calculated 13,600. The density of water is near about 1,000 kilogram per meter cube. So mercury is 13.6 times denser than water. So this is, and then 10, and then 76 by 100, and this comes out to be 1.01 into 10 raised to the power 5, and then kilogram. Fine, that is kilogram meter. That is possible. That is Newton per meter square. Why we use this meter square and other things? You have to reply in the comment box. So this is how. So this is for you. You can do it. Newton per meter square. This is equal to Pascal. If you really want to calculate the pressure in terms of Pascal, Pascal is the SI unit. And how can you do it? So now let me tell you. In case of bar, 0.987 atm is equal to 1 bar. Fine. The SI unit is Pascal. And as this barometer, the simplest barometer, was used by Mr. Torricelli. So to respect Mr. Torricelli, 1 millimeter of mercury will be considered as 1 torr. So 1 atm is equal to 760 torr. This is how you can calculate. And one more very important thing, this vacuum, again in the honor of Mr. Torricelli, this is known as Torselian vacuum. Fine, my dear students. Now let's say somebody wants you to calculate, somebody means your examiner wants you to calculate that if you use water in place of mercury, then what will be the height of the tube which is to be required? So we all know that mercury will be the obvious choice, but yes, they can make this sort of form this sort of problems. So in this case, let's say if water is to be used in place of mercury, so what will be the minimum height of the tube required? Now, my dear students, the pressure will be how much? 1.01, as we are just replacing water in place of mercury. Now look at this. As we can pretty well understand, rho Hg. Fine. So to calculate the same pressure, if you are decreasing density, then certainly you need more height. Pretty obvious. 24 is 6 into 4. If you will increase this 6, then certainly it will goes down. And if you reduce it, it will go up. So if you are reducing density, certainly the height will went up. And as we know that the pressure is 1.01 into 10 raised to the power 5 in sort of pascals, and density will be 10 raised to the power 3 in this case. Why? Like I told you earlier, in case of water, the density of water is 1000, while that of mercury is 13,600. 13.6 more than that of water. So 10 raised to the power 3 into G will be 10, and we have to calculate H. So that is 10 raised to the power 4. So near about 10 into 1.01. Okay. So this is 10.1 meter. So you need a tube of this much height. Let me tell you, in case of mercury, how much it is required? 760 millimeter. Now we need 10 meter of the tube if we consider water as a liquid. So it's better to use mercury. And mercury will help us in many other ways. As it is densest, it will not form vapors, so our vacuum will not be disturbed. Fine. Because density of mercury is highest, and mercury being a metal will not vaporize us. Okay, so this is how you can solve this. One another instrument can be used to observe, to calculate pressure, and that is manometer. When we use manometer to calculate the pressure of a gas, how can we do that? Now, a gas will be put inside a container, and a tube, better known as U-tube, not this one. This U-tube is something else. This is a U-shaped tube, and it is open-ended. We do have close-ended also, but at this point of time, I am describing the open-ended. And we fill this tube with mercury. Now, this gas particle will exert pressure, and the level of mercury will not rises above this point because the same pressure will be exerted by the gas particles. Now what? There will be an atmospheric pressure. Fine. So at this point, what we can say, the two pressures will be equal. What are these two pressures? Pressure of the gas, and this is equal to the atmospheric pressure plus this pressure H rho G, the pressure exerted by this liquid column. Now, as it is mercury, you know about the density. You can observe the height, and then acceleration due to gravity is 10. Atmospheric pressure you can calculate, you can measure, you can measure the external pressure, and with the help of this equation you can find the pressure of the gas. So this is how manometer can be used to calculate pressure of the gas. Now the third thing is temperature, and let me tell you, temperature is the what you can say the most crucial factor which can define the properties of gases. And why? Because kinetic energy of gas particle will be directly proportional to temperature, as it is the foundational base of kinetic theory of gases. Fine, my dear students. So temperature, as we all know, will be measured in Kelvin, and the relationship between degree and Kelvin is well known. And Mr. Charles, when he was describing the interrelation between volume and temperature, at that point of time, we will talk about the absolute scale of temperature. How one factor can enhance, can reduce, and can affect the volume. So these are the measurable properties. Now let's talk about the elementary gas laws. Why I'm using this word, elementary. Elementary gas laws, or what you can say, these are based on the observations only. Initially, when Mr. Boyles was talking about his law, and when Mr. Charles was talking about his law, then it was not explained by the firm base of theories. And these laws are pretty simple. As we know that Boyle's law was simply the interrelation between pressure and volume. That means when temperature is constant, pressure and volume show inverse relation. Look at this. As we know that measurable properties, amount, volume, pressure, temperature, these four can be considered as the measurable properties. And these three, PVT, will be considered as the thermodynamic quantities or identities which can affect the state of the system. If you want to find the interrelation between two, like pressure or volume or temperature, or pressure or temperature, then you have to put the third one at a constant level. So when temperature is constant, pressure is inversely proportional to volume. We all know about it. We all know about these graphs, like what you can say, volume, pressure, look at this. What you can say, PV, pressure, look at this. We all know about these graphs, fine. So I'm moving into the more details of what it actually, what this Boyle's law is actually going to be used for. So like we can say, as the gravitational pull will attract this gases towards itself, and because of this pressure, this density will be very high. So we want to find out the interrelation between pressure and density. How can we find out? As we can say, pressure is inversely proportional to volume. Let's say it is K by V. Just K is generally can be a constant. Okay. Now density will be mass by volume. Fine. Mass is going to be constant for a gas. So what we can say, density is again K by V and pressure is K by V. So what we can predict that pressure is directly proportional to density. Yes or no? So we can derive it from the ideal gas equation. Yes, but I really want to guide you to understand this. So guys, today's lecture is all about, because now I believe that you people are not very keen to watch longer videos. So what I will do, I will design some short videos which can cover a whole lot of idea. And like some of you want me to take these classes in English. Now some of you again are messaging me, sir, please continue with Hindi also. So guys, it's going to be a bit difficult for me to allot this much of time, but surely I'll do it. So what I can do, I will start one separate channel for English, and I will keep this channel for Hindi audience only. But give me a time of day or two. I will start it within about a week, because on 12th of September we have this NEET exam. So many of my students are taking this. So I have to, take these classes up to about 6th or 7th of September. So maybe in the next week, I will segregate these two channels. And I hope till that point, I'm not using pretty difficult English. My English is not that, up to not that level. I'm just explaining you, and I'm taking pretty, what you can say, time to think and speak it out. But don't worry and forget me for my small mistakes in English, as because my English is not that what you can say. But I'm trying it. I'm doing it for you. So this is what we can understand. This is the basics and how we can use these properties: pressure, volume, and temperature. So read it. Try to learn how to find out the pressure of the liquid column at a point. This is going to be used, in most of the occasion. Charles' law is very easy. Volume is directly proportional to temperature when pressure is kept constant. But how this absolute scale of temperature is relevant in Charles' law, we'll talk about it. And in our next lecture, we'll talk about kinetic theory of gases, straightforward, and then ideal gas equation. And kinetic theory of gases is the theoretical foundation of ideal gas equation. So with this, let's meet you in our next class. Take care, guys. Good night.